At 3,900 meters below sea level, the ocean enters what is known as the twilight zone. The light fades to pitch black, and the environment becomes incredibly hostile to mechanical objects. The immediate threat here is hydrostatic pressure. At this depth, water exerts roughly 3.1 tons of continuous compressive force onto a surface area of just 44 millimeters. Under standard watchmaking parameters, a traditional solid block case cannot survive this. The inward compressive loads eventually cause the walls to buckle and implode. The instinctual engineering fix is simply to make the case walls thicker, but steel is dense, and continuously adding mass yields diminishing returns, quickly resulting in an object that is far too heavy and bulky for a human wrist. To withstand over 3 tons of crushing force in a wearable footprint, engineers have to completely abandon the monolithic solid block construction. They need a different way to transfer the load. Rolex's answer to this physical constraint is an entirely different architectural approach called the Ringlock system. The core principle of Ringlock is the mechanical separation of the watch's waterproof external shell from its internal pressure-bearing skeleton. This 3-piece internal skeleton intercepts the crushing forces of the deep ocean and routes them around the delicate mechanical movement ticking inside. The deep sea survives this environment because it doesn't fight the ocean's pressure with sheer mass. Instead, it utilizes an architecture that actively harnesses the surrounding hydrostatic pressure to fortify its own structural integrity. The foundation of this system is a central compression ring. It sits completely isolated inside the 904L steel outer case, acting as the primary load-bearing spine. It is forged from a specialized nitrogen alloyed steel. This specific material is chosen because its density offers extreme resistance to spatial deformation under immense stress. Sitting directly on top of this ring is a dense 5.5 millimeter dome-shaped sapphire crystal made of high-purity aluminum oxide. When the watch descends, the crystal intercepts the water's weight and routes that downward force straight into the compression ring, bypassing the steel exterior entirely. Capping the bottom is a caseback made from grade 5 titanium. It completes the central column, channeling the upward force from the water below directly up into the bottom edge of that same compression ring. The exterior steel shell is merely a vessel to keep the water out. The actual 3-ton load is absorbed entirely by this 3-part internal spine. The choice of grade 5 titanium for the caseback is a highly specific engineering decision based on its unique mechanical properties. Unlike the rigid sapphire and steel components, grade 5 titanium possesses a characteristic of imperceptible flexibility when placed under massive loads. As the depth increases and the water exerts more force, the titanium caseback microscopically flexes inward toward the movement without fracturing. This deliberate, calculated flexion acts as a mechanical vice. The deeper the watch goes, the harder the titanium pushes against the compression ring, clamping the entire 3-piece spine tighter together. This creates a direct physical synergy with the ocean. The environmental pressure itself actuates the seal, meaning the structure mathematically increases its own watertight security as it sinks deeper into the abyss. But inbound hydrostatic pressure is only half the physical equation. There is a counterintuitive secondary threat for deep-sea equipment: outward gas expansion. During commercial deep-sea engineering missions, professional divers live and work out of hyperbaric chambers. To survive, they breathe a specialized gas mixture heavily saturated with helium. This creates a molecular problem. Helium atoms are incredibly small, much smaller than water molecules. Over days inside the chamber, these atoms slip right past the waterproof seals and slowly equalize the internal pressure of the watch with the high-pressure environment of the chamber. The danger arrives during the decompression phase. As the divers return to the surface and ambient pressure drops, the helium gas trapped inside the watch expands rapidly. Without an exit, that internal pressure will violently blow the sapphire crystal straight out of the case. To counteract this expanding threat, Rolex developed and patented the helium escape valve. Built into the case, this spring-loaded mechanism acts as an automated miniature decompression chamber. It safely vents the expanding gas out of the watch when the internal pressure reaches a critical threshold, while keeping the water completely out. submersible dive to the Challenger Deep, the lowest point of the Mariana Trench. Reaching 10,908 meters, the experimental watch on the outside of the submersible was subjected to an astonishing 13.6 tons of localized hydrostatic pressure. Descending to the very floor of the ocean eliminates standard safety margins. It demands absolute structural certainty. To survive that specific dive, engineers custom-built the experimental Rolex DEEPSEA Challenge watch. Looking at the specifications, this chart compares the two watches. The commercial unit on the left withstands 3.1 tons. The experimental unit on the right had to survive 13.6 tons, requiring an increase to a 51.4 millimeter case width and a 14.3 millimeter thick crystal. But if you overlay the cross-sections, you see the most critical data point. The engineers did not invent a new system for the trench. They utilized the exact same internal ringlock geometry, simply scaled up in its physical dimensions. This demonstrates the principle of linear architectural scalability. An engineering solution scaling perfectly as the environmental load drastically increases is mathematically sound from first principles. True engineering elegance in extreme environments is not achieved by building immovable walls against nature. Instead, it is achieved by designing dynamic architectures that harness those environmental forces to ensure their own survival.